Hello everyone, I am Abdelhak Bentaleb, a research fellow at School of Computing, National University of Singapore. Welcome to the presentation for our recent published paper. The title of the talk is HTTP-based low latency live video streaming challenges and solutions. This work is done by myself, Mei Lim, under the supervision of Prof. Roger Zimmerman from National University of Singapore and Prof. Ali and Mehmet from OZU University, Turkey. Our paper is entitled When They Go High, We Go Low, Low Latency Live Streaming in Dash.js with LOL. Basically, this paper is submitted for one of the challenges organized and sponsored by Twitch for the ACM MMC's 2020 conference. In this challenge, we won the second place. This figure shows the end-to-end workflow for live streaming architecture. It consists of two main parts, first mile video contribution and last mile video distribution. For video contribution, we have the following entities: a live source like camera, drone, phone, satellite that creates a raw live video feed, an adaptive bitrate encoder which is responsible for encoding and packaging the raw live video into HTTP adaptive streaming format, denoted by HAS format, including dynamic adaptive video streaming dash or HTTP live streaming HLS for Apple products. Typically, the encoder segments live stream into small pieces termed segments and then generates multiple versions of each segment at various bitrate levels and resolutions, allowing the player to select dynamically the suitable version that fits its observed network condition for the playback. And we have also an origin server that's responsible to push the packaging live or the packaged live content via HTTP push, for example, to the CDN. For video distribution, we have these entities. The first one is CDN Cloud, which is responsible to cache the live segments and distribute them to the HAS players at scale. We have also a transcoder, which is responsible to transcode the encoded live segment if required. This component basically, or this entity, is an optional. The transcoding will be triggered in case of congestion, for example. Here the segment will be again transcoded at a lower bitrate level. This is too important in live streaming because requesting the segments again at lower quality from the origin may cause rebuffering of the player, as well as it increase the latency. The last entity is the HAS player or HTTP adaptive streaming players, which are responsible for requesting through HTTP pool the live segments from the CDNs, performing ABR decisions, which is selecting the best bitrate and resolution that suit the last mile network condition and its playback buffer, and playback the media content. As you can see in this figure, each entity in the delivery workflow is contributing to the end-to-end latency. The end-to-end latency is the latency from the live source until the player. The most impacting entity with 50% of impact is the player, which is mainly because of the buffering, playback, and ABR design. For this reason, we focus on player optimization to reduce the end-to-end latency. The challenge requires solutions to handle low latency live streaming. Solutions should be able to keep the latency to around 1 second while being able to balance the other factors to maximize viewers' quality of experience, commonly known as QoE. Some of these QoE factors include maintaining high video quality, low rebuffering, low latency, and low quality switches. The approach that we take is that we revisit the entire adaptive streaming system and extend selected components that would help us achieve such low latency performance. Our resulting solution includes these three main components. First, we employ HTTP adaptive streaming in the form of an ABR selection module, which allows us to select or switch between ABR algorithms, such as between our heuristic and learning-based ABR, to maximize quality of experience based on the changing environment. Second, the given system also implements chunket transfer encoding, which helps reduce latency but introduces a new problem in throughput measurement, which we will discuss further later. Hence, we also implemented the throughput measurement module that allows for more accurate measurements. Finally, we have adaptive playback, which allows us to control the playback speed to maximize the QoE while reducing latency or maintaining the latency as low as possible. For our solution, we first introduce the QoE model that we use. This model has been adapted for low latency live streaming and is formally written as this equation. The key takeaway here is that there are 5 factors being considered in our model as shown below. The model rewards for bitrate, which translates to video quality, and penalizes for 4 other factors that negatively affects viewer experience, such as rebuffering, latency, deviation in playback speed, and bitrate switches. Next, recall we introduced earlier that we have 2 types of ABR algorithms. They are heuristic-based and learning-based. We chose to implement each of these 2 because they are popular categories for ABR algorithms and they come with different strengths and could perform better under different conditions. Hence, we believe they would serve as good comparisons and potentially good complements in our ABR selection module. Generally speaking, heuristic-based algorithms tend to use fixed heuristics such as mathematical rules or approximations to determine the next best bitrate to stream at. Whereas learning-based algorithms do not follow fixed heuristic and instead attempt to learn from changes in the system environment to make decisions based on the past data. In the following slides, we introduce in greater detail each of these 2 algorithms. For our heuristic-based algorithm, we will open the contributions of FastMPC and adapt its approach to fit our low latency live streaming scenario. The general idea of this algorithm is to calculate the potential QoE across all available options and then select the one with the highest QoE. It consists of 3 main steps which are repeated each time we need to select the next bitrate. First, we permute all possible options of bitrate selection with a look ahead window. In this example, with a window of 5 feature segments and 3 bitrate representation, 200, 600 and 1000 kbps as shown here, then the possible options include those listed in this table. For the second step, we calculate potential QoE for each option. This requires our QoE model as introduced earlier and some additional input data such as the current buffer level and throughput measurements. For each option, we calculate the expected QoE value for each factor and then sum them to get the overall QoE. And for the third step, we evaluate our options based on these expected QoE values. We simply select the one with the highest QoE as the next bitrate. For our learning-based algorithm, we adapt from the idea of self-organizing maps, SOM, which is generally used as an unsupervised classification algorithm. The general idea is that the neurons would, as the name suggests, self-organize across the feature map such that each data point would be appropriately classified under a certain neuron which represents a certain label. This neuron is selected as the closest neuron to the data point by Euclidean distance on the feature map. The neurons move as the video streams and provides new data points to learn from. I will explain a high-level description of the algorithm here, and further technical details can be found in our paper. We first initialize with 3 neurons, which represent the 3 available bitrate levels in our setup. In the first setup, we select the neuron that is currently closest to the optimal state, which is a point on the feature map. This optimal state is determined based on the current throughput and our target latency, buffer, and quality of experience values. Let's say the optimal state is the state over here with the green outline. Here, thus, the closest neuron is this leftmost neuron. In the second step, we update the selected neuron to move closer to the optimal state. This is a standard S1 mapping step to reward the winning neuron, as known as competitive learning. We then retrieve the next segment at the bitrate level represented by the selected neuron. In the third step, after the segment is retrieved and played back, we update the neurons again to learn from our past decision. We first identify our consequent state based on the current latency, buffer, and QE resulting from the previously selected bitrate, and then move the selected neuron closer to it. For example, let's say our previously selected neuron did not do very well, and the consequent state is very far from the optimal state, like this state over here with the purple outline. Then the neuron will be moved away from the optimal state and would be less likely to be selected in the subsequent cycles. Similar to our heuristic-based ABR, these steps repeat each time we need to select the next bitrate. In selecting a suitable ABR for the job, there are multiple approaches that we propose. For a start, we could select based on how much certainty we have on the system and environment. For example, if the system dynamics are not predictable or the QoE model is not clear, then learning based tends to be better since we do not need to fix our heuristics such as the QoE model. Alternatively, if we have multiple ABRs implemented as in the case in our paper, we could conduct extensive experiments to evaluate the performance of both ABRs, which is what we have done in our evaluation section. This approach is somewhat more tedious, like brute force, but is also useful now as we begin to explore the idea of ABR selection or switching, because these experiments would help us better understand the strength of either ABR under different conditions. Then, with that knowledge, we could explore the possibility of dynamically switching between both ABRs based on changing user requirements, media, or environment factors. We hope to explore this as a part of our future work. Next, we introduce our playback control module. The goal is to adapt the playback speed to reduce latency while not risking rebuffering. For example, too fast playback speed can quickly bring down latency but would delete the buffer very quickly and risk rebuffering. We use heuristic-based approach with the configurable parameters. This table provides a worked example. First, the system predefines the target latency, safe buffer level, and allowable playback range. And let's say we have these 3 scenarios with different latency and buffer levels. For example, in the first scenario, if the current latency is less than the target latency, then we could slow down the playback, which is good for building up the buffer, so that if the latency starts to grow above the target latency as seen in scenario 2, then we would speed up the playback to say 1.4, so that we can quickly bring the latency down. However, if the buffer is below the safe level as seen in scenario 3, then we dampen the speed up to say 1.31 to reduce the impact on rebuffering. Next, we introduce our throughput measurement module. As mentioned earlier, the use of chunking transfer encoding could help reduce latency for live streaming, but also introduce a problem with existing throughput measurement methods such as ACTA due to the presence of inter-chunk idle periods. To visualize this problem, we look at this scenario where the chunks of a segment are generated with idle times in between, such as between chunks 5 and 6. If we were to measure the download time on a segment level from the first to last chunk, such as from B1 to En, assuming n chunks, and use that segment download time to calculate throughput, then these idle times could be uh, erroneously indeed and underestimate the actual throughput. To fix this issue, we can see that instead of measuring download time at a segment level, we need to identify the actual chunk download times as annotated in red here. Hence, we propose a two-stage algorithm that uses the latest fetch API to improve over ACT. In the first step, chunk boundary identification, the algorithm identifies the beginning and the end time of each chunk downloaded by capturing the move box in fragmented MP4 data. Then, thanks to the fetch API, our algorithm is able to use the streaming response body object, which allows us to track the progress of chunk downloads and parse the chunk payloads in real time. In the second step, idle periods filtering. We then use this chunk timing information to remove the inter-chunk idle periods from the measured download time. We also employ other enhancements such as ignoring the first and the last chunks to avoid any transient outliers. We have implemented our solution in Dash.js and our code is publicly available on GitHub. The code files changed are listed over here. We also evaluated our solution to answer these two questions. The first one is, how do heuristic and learning-based algorithms perform at low latency? Does our throughput measurement module perform well? To answer the first question, we ran multiple automated streaming sessions to derive the average QoE scores for each algorithm under 5 different network profiles provided by the challenge. We show results for 2 of the network profiles here. Note that these network profiles emulate changing network conditions such as cascading bandwidth that could drop to as low as 200 kbps. Hence, the quality of experience scores could at times drop to negative values. We note that our learning-based ABR tends to achieve higher overall QE than our heuristic-based, especially for the two network profiles here, profile cascade and profile intra-cascade. To understand the performance difference better, we look at the session metrics collected. We can see that the higher QE score largely due to the lower number of bitrate switches in learning-based as compared to heuristic-based, which translates to a more stable stream. Intuitively, this is likely because the learning-based algorithm tracks 4 dimensions with 4 different weights, including latency, buffer, and QE, which makes the algorithm more sensitive to change in any one of these factors. Hence, it could pick up the bandwidth changes very quickly and allow the stream to better handle sudden bandwidth drops. However, We also know that heuristic-based has its own merits in the sense that it could potentially achieve better results on some QoE factors, such as rebuffering. So this suggests that different ABR algorithms do have their own strength, and hence having an ABR selection module that could select the best one based on changing requirements and environment conditions may help us leverage this ABR better. To answer the second question, we also collected the throughput measurement made by our implementation and the Dagia's default implementation and compared them against the true bandwidth values as provided to the network simulation tool. This figure on the slide plots the measurements across one sample run for each network profile. We can see that the Dagia's implementation tends to error at high bandwidth region, where chunked transfer encoding enabled transfers are more likely to occur. This follows our earlier discussion on how CTE or chunked transfer encoding may cause issues in existing throughput measurement methods. We also calculated the average measurement error using multiple runs across all 5 profiles and found that our implementation could bring the average measurement error down from 253% to 21% of the true value when compared to the Dash.js implementation. This marks the end of my presentation. Again, our code is available on GitHub, so please do check it out and feel free to reach out to us if you have any further question. Thank you.